Hello, and welcome back to another IB Math speedrun with me, Vince. This is the final speedrun of today, and we'll be covering numerical ways to solve, ordinary differential equations. So let's jump right in. So we've covered a variety of ways to solve different differential equations, but not all. These aren't sufficient for solving all differential equations. And so we still need numerical methods to solve an equation. So the most common one that we can use is called Eulers Method. And it is when we have a first order differential equation in the form dy over dx is expressed in a function of x and y. This works by selecting an initial point of x is 0, y 0. And then we need to use recurrence formulas to generate the next point. So x of n plus 1 is equal to x of n plus h, and y of n plus 1 is equal to y of n plus h times f of x of n, y of n. With, of course, h is the step size, so it's how accurately we want to measure it. If we want to use smaller intervals, we decrease h. It's like decreasing h in the limit. If we want to use bigger intervals, which will be maybe more inefficient, but it might be faster, then we can use bigger h values. And if we plot these points in a smooth curve, then we can generally find a gradient at that point. So let's jump into some questions involving this, and we only have two. So first, use Euler's method with a step size of 0.4 to approximate the solution. Remember, if you use Euler's method, we're only approximating the solution. And so we need to solve this differential equation. We're given that y of 1 is equal to 2, and we need to solve it at x equals 3. Now, of course, we could solve this equation normally, but it's good to give us practice for using numerical methods on an equation that we're familiar with. So, how would we use his method? Well, we have f of x and y is equal to 2xy, and we'll start at y of 1. So when x equals 1, so this is the 0th step. X equals 1. Let's put as the number of steps. The number of steps. This will be x. This will be y. We're given that y is equal to 2. I think it's 2 at this point. And we need to get the value of 2xy, which is equal to 2 this is 4. And then for the next recursion, we get that the step is equal to 1. We're stepping up in increments of 0.4, I believe. Yep, 0.4. So this will be 1.4. Our y value will be equal to 2 plus 0.4 times this new gradient, which is 4, which is equal to 2 plus 1.6, which is equal to 3.6. And so the new value of 2xy, which is 1.4 times 3.6 times 2, is equal 1.4 times 3.6 times 2 is equal to 10.08. Okay, next step, we go to the second step, which is at 1.8. So this will be equal to 3.6 plus 0.4 times 10.08, which is equal to times 0.4 plus 3.6. This is equal to 7.632. And so this next one will be 2 times that times 1.8. 2 times 7.632 times 1.8, which is equal to around 27.48. Now for this next one, we have Stop lagging. We have our next step at 3. Let me just check that we're right so far, but I think we are. Where are we? We are at 8i. Yep, so I think we're okay so far. So next step is, I believe, 1.8 plus 0.4, 2.2. And so this will be 7.632 plus 0.4 times 27.48, which is equal to, plus 7.632 is equal to around 18.62. And so if we multiply this by 2.2, we get 4 times 2 again. We get 81.9 as the gradient. And then finally, we have our fourth step. Actually, not finally. We still have some more. Next one is 18.62 plus 0.4 times 81.9, which is equal to, plus 18.62. This is equal to 51.39. And so if we multiply this by 2.6 and we multiply by 2, I'm getting 267.3. Actually, these numbers are getting quite big. Let me just check. Y prime equals 2xy. Y of 1 is equal to 2. And we need to solve it at x equals 3. Okay, let's keep going. So for the final step, at 3, we get 51.39 plus 0.4 times, why did that zoom in? Times 267.3. And so this is equal to 106 plus 51.39. So our final answer will be 158.3. So this is the approximate y value at this point. So that is the solution to this differential equation. Next, we have the final question of today, which is use Eulers method again to find approximation of the value of y when x equals 0.3, given that dy over dx is equal to e to the x plus 2y squared, and y at 0 is equal to 1. So we need to find y when x is 0.3, given that y of 0 is 1. So I'm going to use a step size of 0.1 to do this. So we set up our table again, number x, y, and f of x, y. At 0, we have y, x is 0, y is 1. F of x, y is equal to e to the 0, which is 1, plus 2y squared, which is 2. So this will be 3. Now next step, we're going up 0.1. And then for this y value, we have 1 plus 0.1 times 3, which is equal to 1.3. And so f of xy will be equal to e to the 0.1 plus 2 times 1.3 squared. So this should be around 4.49. Okay, next step. We get 2, this is 0.2 now, and we have 1.3 plus 0.1 times 4.49, which is equal to 0.1 plus 1.3 is equal to around 1.749. So I'll call it 1.75. And then so if we do the function of these, if we do the function here, we get 2 times this squared plus 0.2e. So e to the power of 0.2, which is equal to 7.34. And then finally, on the third step, where we have 0.3, where we need to find y, we get 1.75 plus 0.1 times 7.34, which is equal to plus 1.75. I got 2.48 as the final answer. So this is correct. 2.45, the book says it could be a rounding error. So yeah, this is a good approximation for the y value at that point. So that's all for the speedrun. I hope you enjoyed it, and I hope to see you in the next one. See you then.